Synthesis examples for test number 3 as promised. So in this first one, it's important to count the carbons because your eye can fool you, because this chain kind of looks like this chain, except this has 3 carbons and this has 4 carbons. And so what we need to do is add 1 carbon, and ultimately that needs to be a new carbon-carbon double bond. We're not adding 2 carbons, so we can't just stick an acetylide anion on there and then reduce it. So some of the new chemistry that we've learned in this chapter is that if we do a Hofmann elimination of an amine, we can make an alkene, and we can get this primary amine plus a carbon by adding a nitrile and then reducing it. So the amine comes most immediately from the nitrile, and then the nitrile comes from an SN1. So we're going to take our alkyl halide, add sodium cyanide, do an SN2 reaction. That gives us the nitrile. We now have 1, 2, 3, 4 carbons. And we can reduce this several different ways, including excess lithium aluminum hydride, followed up with water to make the primary amine. And then we do the Hofmann elimination with the infamous exhaustive methylation, followed by an exchange of the halide to hydroxide and an elimination to give the Hofmann alkene, which in this case is the only regioisomer you can get. So this next one, if we count carbons in the reactant on the left, we have a 5-carbon ring plus a 6th carbon here. Here we have a 6-carbon ring plus a 7th carbon. So we're going to have to do something to add a carbon. The other thing that's more obviously going on here is we start with a 5-membered ring and we end up with a 6-membered ring. And the only way we have of directly expanding a ring would say be a Baeyer-Villiger oxidation, but that's going to stick an oxygen in there, and we really don't want to do that because then we have an oxygen we didn't need. But what we can do is we can open this ring. We can open this ring via ozonolysis and then do an aldol to close it. That'll give us this alpha-beta unsaturated compound that we can then add our alkyl group to. So you're opening the ring and then closing the ring. So going forward, we do the ozonolysis with the reductive workup to give us this compound. And I numbered the carbons here and then in these 2 compounds that are hopefully the same compound. And then we do our aldol condensation, making sure to heat it up so that we get a condensation and not just a reaction. And then we can alkylate the beta group relative to the carbonyl with a cuprate. So this next one, number three, you might think you could just stick that alkyl group on there. But the problem is that if you try to make, say, the enolate of this and then alkylate an alkyl halide, the alkyl halide that you're going to have to use is tertiary. And since this is an SN2 reaction, we know from Chem 21 that this is not going to go. So we need some other way of making a carbon-carbon bond. And one thing that we could do is make this compound. So we're going to make this as the new carbon-carbon bond using a directed aldol. So we're going to use acetone and the cyclohexanone. And then once we have this compound, we can once again use our cuprate to alkylate. And I chose to use acetone as the carbonyl instead of butanone, and then alkylate with a methyl cuprate, just because I thought we might get in less trouble with acetone, although it probably doesn't matter at all. So again, here's our new carbon-carbon bond, and then we're also going to add that piece. So we're going to put on make that bond, and then we're going to make that bond. So looking forward, again, this has to be a directed aldol because the species that we want to have act as the carbonyl has alpha hydrogens and has a carbonyl that's of the same reactivity as the other carbonyl. So we make the enolate of this, we add the acetone, and you want to do something to make sure that it eliminates. You could probably just heat it up, or you could add acid and heat it up and make sure. Doesn't really matter. And then we just need to add our ethyl cuprate and then follow that up with hydrolysis to give us the final product, which is hopefully the same. No, it's not. I drew it wrong. Let me fix that. So there's the final product, the correct final product. So then in number 4, we start with a benzene ring, which clearly is going to take us back to test number 2. And so again, kind of trying to look at this retrosynthetically, we can think about adding this in pieces. So we can add that piece first and then that piece. And again, thinking retrosynthetically, if we had this ketone, so kind of this piece with the first carbon chain added, and then we did a reductive amination, that would give us this compound. So now what we have to do is make that. The carbonyl is not in the right place for an acylation, but we could get this via a Grignard of the benzene ring and then that particular epoxide. Now, sometimes the epoxides other than epoxide itself don't work well with Grignards. We're going to assume at our pay grade that it does. You can do it with epoxide, although it gets a little bit touchy. So again, Chem 22 pay grade, we're going to go ahead and use this epoxide and add all the carbons at once. But first, we need to start out, we need to brominate our benzene ring, make the Grignard, add the epoxide, which is going to be that epoxide, and then add water to protonate the Grignard, and that's going to give us this alcohol. Technically, you could oxidize this, you could oxidize a secondary alcohol to a ketone using almost anything. I chose to use one of the milder ones because you might remember that there's a reaction whereby you can take a regular alkyl chain and oxidize it to a carboxylic acid at this carbon to make benzoic acid. And I don't think we really want to do that, so I picked a milder oxidizing agent. And then once we have our ketone, then we just do the reductive amination. So in the penultimate one, we start with malonic acid. Not malonic ester, but malonic acid. And we need to make this thing, right? Again, think retrosynthetically. So the ways we have of making tertiary amines are by reductive amination or reducing an amide. I chose to reduce the amide, so this is the amide that you would reduce, and that amide is going to come from this carboxylic acid, and this carboxylic acid you could get by a malonic ester synthesis using a dihalide. And in the reaction going forward, I showed where the different carbons come from. However, in order to get this going, the first thing that we have to do is take the malonic acid and make the ester out of it. This is not going to work if we use malonic acid because when we add the base to malonic acid, we just pull the proton off. So we start with our malonic acid, we esterify it. And notice I've marked that carbon with an orangish dot. And then we go through the malonic ester synthesis. So I use sodium methoxide because I happen to make the methyl ester. Then I add this dihalide, and you can see in the final product I indicated the dihalide carbons in purple and the malonic ester carbon in orange. And we do the hydrolysis, which is going to then give us this compound. I did something similar when I did the synthesis examples from the end of that enolate chapter. Can't make an amine directly from an acid, from a carboxylic acid, because you'll just get proton exchange. So we need to make the acid halide, take the acid halide, add excess amine, and the point of the excess amine is that we get as a byproduct the salt of the amine. So one equivalent of the amine is sacrificial in order to neutralize the HCl that's produced. Then once we have the amide, we can reduce it. There's probably a way to do this with a sort of acetoacetic ester synthesis, but I think one end would need to be an aldehyde. So in other words, you need to have that aldehyde, and then I think that would work too. So finally, we need to take this aldehyde, this alpha-beta unsaturated aldehyde, and add a methyl group to the beta position and an ethyl group to the alpha position. And then we have to do some chemistry to convert the aldehyde into an ester. And we could probably do that in almost any order. So in other words, we could take the aldehyde and get it to the ester and then do our alkylations, because these alkylations should work fine with either the alpha-beta unsaturated aldehyde or the alpha-beta unsaturated ester. So in other words, we could use take that ester and we could do the alkylations on that. I didn't choose to do it in that order, but that would be fine. So working forward, when you do the alkylations of the alpha and beta carbons, you can do a conjugate addition to the beta, which then gives you an enolate here, and then you can alkylate that. That's going to give us this aldehyde. And then we can oxidize this anyway. I decided to use MCPBA because it was one of the reactions from the end of the aldehyde ketone chapter. And then we need to esterify this. A Fischer esterification like we did in the previous problem would be fine. For versatility, I decided to do this by converting the carboxylic acid into its anion and then doing an SN2. Make sure you understand the difference between these alkyl groups, that this is acting as a nucleophile and this is acting as an electrophile, because sometimes that'll help you to sort through what's going on.